So I'm going to talk today about joint work with Stephen Bigelow, Emily Peters, and Noah Snyder. And I'll just say right at the beginning, actually, that everything we do here follows very closely some work that Emily Peters did on the Haagerup planar algebra. And she has a great paper that's already out explaining all these techniques. And we're basically just doing a slightly harder case here to get through some time. Let's get started. Okay. First of all, I'm going to just give you a brief overview of subfactors for native speakers of tensor categories. I'll just give a very quick dictionary so that you'll understand all the pictures that I draw later in the talk. And after that, I'll talk about a classification result for subfactors. With the index, then you can get quite some results. And then I'll give an overview of how you might try and construct planar algebra, or construct subfactors using planar algebra techniques. And then in the last section, I'll do the actual details for this mysterious extended Haagerup subfactor. And that has some pretty cool string theory and some nice pictures to do it. But first of all, how do we translate? Well, the theorem, due to a bunch of people, Popper, Rockniani, Jones, I guess, various bits of it, extreme finite index 2-1 subfactors correspond to unitary spherical categories, or tensor categories, but with two types of tensor product. And a chosen generator, it's X, which is a left A object and a right B object. So when we say there are two different tensor products, that is, every object is a left label and a right label, and you can only take tensor products when the labels match up. This might sound like a funny thing, saying with a chosen generator X, but really it's somehow the essential difference between thinking about unitary spherical tensor categories and planar algebras. Looking at the tensor category from the point of view of a particular generator suggests different techniques, and you'll see what I'm talking about as we go through. Let's just finish the dictionary here. The index of the subfactor, A inside B, is just the square of the quantum dimension of the chosen generator X. People will talk about the principal graph of a subfactor. There's actually a pair of principal graphs. So people say principal graph and a dual principal graph. And this just tells you the tensor products of an arbitrary object with your chosen generator on the right. And I guess there are two cases here. You can, if V is a right A object, you tensor on the right X. But if V is a right B object, you have to tensor on the right X. Now, you can take the even part of one of these A-B tensor categories, which is just the subcategory of all the AA objects. It's called the even part. And of course, you can alternatively take the BB objects. And that's the even part of the dual is what people would usually say, I guess. Now, the double of the even part is, of course, a modular tensor category, just because doubles are. And the things to say here, well, first of all, it doesn't matter which of the two even parts you take, because just having the subfactor and this and these mixed modules, these AB modules, gives you a Morita equivalence between the two different even parts, and so that means the doubles are the same. We only have one double coming from each subfactor. And these modular tensor categories that you get from some of the strange examples of subfactors look kind of weird, and there's some evidence that they might be exotic. That is, they don't come from quantum groups by some list of construction. They don't. There's this paper of Conrad and Rob that does some of that. But there's probably lots more to be said in this direction about describing the modular tensor categories from subfactors in terms of other constructions. Here's another version of another dictionary, this time telling you how to translate pictures between the two different worlds. The left column is just the standard setup. So in this picture here, F, G, and H are meant to be morphisms in the category. So for example, F up here, you should think of some morphism from B, tensor C dual, because the arrow is going down, tensor, well, whatever label is missing on that strand, and so on. And you'll notice that in this picture, I haven't distinguished the sources and targets of morphisms. So maybe you should think of these F's and G's as H's as maybe being elements of some space of invariance in the tensor category. Because we're in a spherical tensor category, the distinction between sources and targets isn't really relevant, so it's nice to Over on the right-hand side, things are a little bit different. First of all, the edges aren't oriented, and moreover, the regions are alternately shaded or unshaded. And these shadings correspond to the left and right A and B labels. Where on the left-hand side you have many Hom spaces between arbitrary tensor products of objects. On the right, there's just a family of vector spaces, these pk, maybe ignore the plus or minus. pk is just a vector space of all pictures that you can put in a disk with k boundary points, and the regions alternately white and black. Oh, okay, sorry. If I say that, I'll tell lies later. Because of this shading here, all of the disks have an even number of boundary points automatically, and so our convention actually is that pk is the disk space with 2k points around that. And the plus or minus here, well, you have two different spaces depending on whether the marked point is in a shaded or unshaded region. That just tells you where to start reading a circular tensor product. Okay. Now, how do you go back and forth between these two different types of pictures? Well, if you have a spherical tensor category with two sorts of objects, with two sorts of shadings, but maybe many objects, you can choose your favorite generator and look at that, and that tells you, well, let's go to the subcategory, the full subcategory where the objects are just tensor powers of your favorite generator. Every object appears inside that if it really is a tensor generator, but we don't allow those as objects when we think in the planar algebra. So how do you go back again? Well, if you have some tensor category where the objects are just powers of x, you can always form the idempotent completion. Just throw back in all of the objects, or throw back in as objects all of the idempotents in this category. So if one of these tensor products breaks up as a direct sum, these summations might not exist in this setting, but they always exist as idempotents in the spaces here. So you can go back by taking that. Hopefully, the features I draw will mostly move around to immediate sense. Okay, so the classification result up to index 3 plus square root 3. So this means that in the category there's some object whose dimension is smaller than the square root of 3 plus. In 1984, Haagerup published this list of possible principal graphs of subfactors of index less than 3 plus root 3. Now, there's one family here. These are all the same graph except the initial arm has different lengths, changing mode 4. There's this single graph here, and there's another family of graphs. Again, just the initial arm is increasing in steps of 1 4. Now, the first two, well, these ones highlighted in green here, were constructed by Haagerup and Haagerup and Haagerup in 1999. And then a little bit later, Bish, and then very recently, Seder and Yasuda, have ruled out infinite families. Bish ruled out this entire family of possible principal graphs here. And conceptually, it's very simple. He just shows that there's no possible fusion algebras extending the tensor product encoded in that graph. And then Seder and Yasuda have a great paper where they use a bunch of number theory to show that all of these graphs from this guy out are impossible. That leaves one guy in the middle, which until recently no one really knew whether it existed or not. And so today we're going to fill in this last step of the classification to show this guy really exists. Now, I just want to say a tiny bit about the previous constructions that have been done. Just remind you of the words. So Seder and Haagerup find a biunitary flat connection. So this is in Opniani's Haagerup formalism. And Ikeda, in 1998, actually provided some numerical evidence that this last remaining graph really did have a corresponding subfactor. He found a flat connection by a bunch of numerical calculations, and he says it exists up to 10 to the minus 19. But I think everyone immediately took that as really good evidence that it was there. I mean, he couldn't have got into results if it wasn't there. Now, well, maybe. Our techniques are totally different from these ones. And I'll just say here that, like Ikeda, we do use a computer in the course of our construction. And in fact, in finding a particular generator, we're going to need to find a as I'll explain later, we really use a computer a lot. I mean, a day of computer time. But in the end, there's really very little of the computer being used in the proof that I'm going to explain to you. There are some really large matrices we need to multiply and then take traces of, and we still need a computer to do that for us. We're not multiplying 1,000 by 1,000 matrices by hand. But that's all the computer does, and it's using it exactly. Okay, so how does one construct a planar algebra? Well, this is sort of the big idea. Now that we know about how to translate subfactors to subfactor language into planar algebra language, we can just give scheme theoretic instructions of subfactors. That is, we can write down a generator, that is some box, and then write down a bunch of relations for planar combinations of this box. And this talk is going to illustrate a technique for showing that these sort of constructions really work. Now, if you're going to write down generators and relations, you need to have some idea of what sort of generators and relations to write down. And Jones's work in two papers, they're, I think, both on his website, but not on the archive. On annular and quadratic tangles, actually gives you an awful lot of information about what the generators and relations in a planar algebra should look like. And most of this information comes directly from the principal graph. So you can learn quite a lot very quickly. And as I said before, Emily Peters has done this for the Haagerup subfactor. And there's an archive reference there. If you should go look up if you're interested in any details that I say in this talk. Okay, so what is this information that we get about generators and relations by thinking about planar algebras? So first of all, we need this notion of the annular temporally category. So this is temporally leave is just usually string diagrams in a rectangle where you can remove a loop for a factor of delta. The annular temporally category is the same diagrams with the same relations but drawn in angles. Now, if you think about the annular temporally category, you can quickly work out that every representation in this category breaks up as a direct sum of representations generated by lowest weight vectors. So our lowest weight vector, tk lambda, is something satisfying these relations here. First of all, any way of capping off the generator producing a smaller box, so here I guess k is 4 in this case, you've got 8 boundary points. So capping it off takes you from P4 down to P3. Any way of capping off is 0, and you're a rotational eigenvector, then that's the lowest weight. Okay, since the planar algebra itself has to be a representation of annular temporally leave, act by these diagrams on any element of the planar algebra, the whole planar algebra has to be generated of elements like this. And we're going to start with let me say a little bit more about annular temporally leave and some terminology we'll use later. If you have a low weight vector, let's write ATL plus 1 of t for the annular consequences of t one level up. So that is, here t is in P5, it has 10, my numbers are all wrong in the text there, sorry. Here, I should have said t is in P4, and we're talking about the annular consequences in P5. So t here has 8 boundary points, that's something in P4. But now you can add a cup anywhere around the boundary, produce an element in P5. Yep. I'm sorry. How many annular consequences should there be? Sorry, I'm not sure.
You just say P4 because there are 8 boundary points.
Yeah.
Sorry. Yes. So T here is the lowest weight vector. T lives in P4 because it has 8 boundary points. And now we're taking various images of T in the next space up. So we're looking at this element is in P5 while T was in P4. And the lovely lemma about representations of the annular temporally leave category is that as long as delta is less than 2, this fails in the ADE cases when you're below index 4, the annular consequences of a lowest weight vector, the annular consequences at any height, so we can add lots of nested cups all around the boundary, they're all linearly independent. And this is great because it lets us count the dimensions of a representation of annular temporally linear. We know we have a low weight vector for some value of k. We can compute the dimensions of this representation in all of the higher disk spaces just by counting the ways of inserting caps. Okay. Knowing now the dimensions of annular temporally linear, and knowing that the whole plane of algebra breaks up as these representations, we can deduce that there are certain relations between quadratic tangles. So just by counting dimensions in the extended Haagerup planar algebra, so you can work out the dimensions of P at any level just by looking at the principal graph and counting paths on that. We can just sort of do a lowest weight decomposition and see that as a representation of annular temporally, it starts like this. There's the representation generated by the empty picture and all of the consequences you get then are just in temporary lead. But then there's another generator with 16 boundary points and eigenvalue -1. So when you rotate by 2 clicks, it changes by a sign. And then there's more stuff. I should say here that the title is quadratic tangles. This really isn't something from Vaughan's quadratic tangles paper. This is still sort of the annular angle sort of idea. If you want to know how I knew that eigenvalue was -1, then you should read his quadratic tangles paper. And then there's more stuff. Okay, so let's have a look at this. T has 16 boundary points. So let's look at this guy. We're join 2 copies of T up by 8 strings. This still lives in P8. And that means that it's got to live in, well, the annular consequences of this, that's all temporally leave, and, well, and some multiple of the generator of this guy. That tells us that this guy, T squared, is just temporally leave plus T. Coefficients. Let's look one level up. Let's look at 2 T's connected by 7 strands. There's no lowest weight vector in P sub 9, and so this thing here must be a linear combination of temporally leave and the annular consequences of the generator T. So there's going to be some linear relation there that lets us replace 2 T's with a single T, as long as they're connected by at least 7 strands. And now let's look one level up. Let's connect 2 T's by 6 strands. There's still 20 strands around the edge, so we're in P10 now. We know that in P10, all that there are annular consequences of the first 2 low weight vectors, and this single new lowest weight vector in P10. Now that means that these 2 guys here, well, some linear combination of those 2 guys must just be annular consequences of all this stuff. Well, I mean, I'm lying a little bit. Maybe I can't guarantee that there isn't some linear dependence between these things, but that would be a very special case, and you can see that things go wrong. Okay. So now what this says is that if you can see 2 T's connected by 6 strands, you can replace them by 2 T's also connected by 6 strands, 1 plus 4 plus 1, but in a slightly different way, at the expense of lots of terms with fewer T's. Okay, so now we have some idea of what sort of relations we have to expect for any generator of the extended Haagerup algebra. Suppose I give you such a generator and I can show that it satisfies these sorts of relations. How do we tell that it really is what we want, the extended Haagerup planar algebra? Well, it's kind of easy. If we can show that the planar algebra I've given you is a subfactor planar algebra, maybe I should have said this earlier, so the axioms we need for it to be a subfactor planar algebra are that it's unitary, that it's spherical, and the dimension of the 0 space is 1 dimension. That is sort of the tensor identity is simple. If we can show it's a subfactor planar algebra with the correct index, then Haagerup's classification guarantees it's got to be the right thing. You can't get wrong. But if I give you an explicit planar algebra, you can also compute the principal graph by hand, although it's a lot of work and we certainly haven't done it. So you could prove that this does have the right principal graph without appealing to the classification. Hopefully. Maybe someone enthusiastic about it. Okay. So we're left with the problem of how do we know that some planar algebra is a subfactor planar algebra? Okay, I guess I should have. Here's a really important thing. If I give you a planar algebra specified by generators and relations, your first question should be, are the relations consistent? Does the whole thing just collapse down to 0? So we've got to check that first, that there really are non-zero things. is the planar algebra unitary, and is the dimension of the zero box space 1. Saying the dimension of the zero box space is 1 is just saying that you can take any closed diagram, and the relations that you've specified are sufficient to evaluate everything in terms of a multiple of the empty diagram. How do we answer these questions? The first two are really hard from a scheme theory point of view, so we have to do something else. If we can find an element T inside a big planar algebra, not necessarily a subfactor planar algebra, but some subfactor planar algebra, and we know that big planar algebra is unitary and spherical, then we're guaranteed that the subplanar algebra generated by T is still unitary and spherical. So that's going to be our strategy, and there's unfortunately an obvious place to look from this bigger planar algebra. Every time you have a subfactor planar algebra P, you can compute its principal graph, so write gamma of P, I guess, and there's a thing called a graph planar algebra, which is just depends on a bipartite graph. Give me a bipartite graph, I'll give you this big planar algebra. And the theorem is that every subfactor planar algebra is some subalgebra of the graph planar algebra of its principal graph. So we're going to look for some element of this graph planar algebra. The subalgebra generated by it will automatically be unitary and spherical, and then we're left with this last problem. Can we evaluate closed diagrams? And if we, well, that's going to require some clever scheme theory. If we can, we have what we want. Let me briefly tell you about the graph planar algebra. So given a bipartite graph gamma, the spaces in the graph planar algebra, the kth space is just all linear combinations of length 2k loops on gamma. I guess there's a technical point if you're looking at the k plus space, then the loop should start at an even vertex in the graph, while if you're looking at a k minus space, the loop should start on an odd vertex of the graph. And there's some action of the temporal unique operad on these spaces, which is pretty simple. I mean, it's sort of a state sum model, and there are some coefficients that depend on the perimeter of the asymptotic of the graph. The details of that won't actually matter. The relatively easy theorem is that the graph planar algebra is always unitary and always spherical. It's not a subfactor planar algebra because its zero box space is way too big. GPA 0, well, let's just link 0 loops on the graph that are based on even vertices. So it's just a number of even vertices. Of course, that's more than one in most graphs. Just to give you an idea of how big these guys are, here H is meant to stand for Haagerup, and if you look in the 4-box space for Haagerup, which is where the generator for the Haagerup planar algebra should live, that's a 375-dimensional space. So to construct Haagerup, you're looking for some special element of that. And for extended Haagerup, you have to look in the 8th space to get a box with 16 strands. You're trying to find some particular element of 150,000 dimensional space. It's somewhat more painful. So let's start looking for this element now. Oh, sorry, I guess that's a typo there. This 16 should be an 8. We're looking in the 8-box space. 16 points on the boundary. Okay. We know that we were looking for a generator with rotational eigenvalue -1. When we look at just the equations for a lowest weight vector, we can solve these relatively easily on a computer in this 150,000 dimensional space. And we get down to a 19-dimensional line. Things are already looking a little bit better. Now, I showed you a bunch of relations that had to be satisfied by t squared with 8 strands or 7 strands or 6 strands connecting them. And using any of those, you can very quickly deduce that actually t squared is on the nose equal to the 16th transcendental eigenvalue. Now, looking at all of the coefficients of this guy in the graph planar algebra, that's 150,000 quadratic equations on T, and well, obviously that's massively overdetermined, and if you don't believe in extended Haagerup, you shouldn't expect there to be a solution. But, well, by ad hoc methods, I've said here, which translates into several days of staring at quadratics and solving some by hand and solving others by Newton's method and then guessing plausible-looking exact solutions from what Newton's method showed up and a real zoo of stuff. We find a solution. Notice I didn't get to write on this slide find a unique solution to these quadratics because we use such ad hoc methods that we couldn't prove that there's nothing else. We might be able to fix that. Okay, we found something. And either this thing generates extended Haagerup or we do. Okay. So at this point, forget what I just said about all these days of work of playing with a computer and trying to solve quadratics by hook or by crook. We've got some guy, and we have an explicit description that's relatively easy to write down, even though it's in this huge vector space. It's not so bad. Actually, let me just flick through the slides, show the generator just so you can see what sort of thing it looks like. We need to give its value on all these 150,000 loops. So it all comes down to this part here. It's the trick that lets you write it down personally. If gamma is some path on the principal graph, it spends some amount of time in each of the three legs of the graph. Remember, the graph is just a trivalent vertex with legs of different lengths. And so we can just produce this word in 0, 1, 2 that just tells you the amount of time it spends in each of the three legs. And it turns out the coefficient of a path basically only depends, well, except for some sort of easy factors, on the time it spends in different legs. So I'm just going to have to tell you these numbers, p sub gamma hat. And so you write down 21 of them. They're very mysterious numbers. They're very mysterious, but I mean, they're low-degree polynomials with small integer coefficients. It's not as bad as it could be. And then you extend those 21 definitions to some other definitions for arbitrary words in 0 and 1, and then by some more rules to all these words, and that tells you the generator explicitly. Okay, so back here. Once you've written this down explicitly, you can check by hand the thing you produced really is a low weight vector. You don't need a computer to do that. From the nice compact the description I gave before, you can really do it yourself. We know the subalgebra is non-trivial and unitary. You just need to check that those diagrams can be evaluated. So, let's get our hands dirty and do some real scaling theory. It's only really at this point that what we're doing becomes specific to extended Haagerup. So far, it's just sort of been a general model for constructing linear algebras for any reasonable graph. From this generator, first of all, I'm going to compute 6 numbers. Here's where we take a couple of hours of computing time, multiplying matrices and computing traces. So t squared and t cubed and t to the 4th here, these are just the products. Those powers there mean connecting up t's by 8 strands. Okay? So these powers are still the same size boxes as t is, and the trace just means goes up this way. That's t squared. Okay, so we calculate these numbers, and then these 3 numbers, rho to the 1/2 is the one-click rotation of t. So if t is a guy here, we bring one strand that way, one strand that way. And notice now that if t was unshaded in this region, it's now shaded in this region. So the half-click rotation lives in a different space in the planar algebra. But again, we compute some traces and get some more slightly mysterious numbers. We're done with the computer. You just have to be a dedicated user of Bessel's inequality, and you can derive these relations. What do they look like? On the left-hand side, here we have an S with 16 strands coming down, an extra arc over the top, and then an 18-strand Jones-Venzel anapode on the bottom. Unfortunately, these pictures don't have strands coming down to the bottom there, but they really should. On the right-hand side, there are 2 S's connected by 6 strands, and then a Jones-Venzel anapode on the bottom. And these 2 terms are just equal up through multiple. Why are things like this true? Well, imagine now taking this F18 and expanding it in terms of all the Templer-Mead diagrams. Nearly all of the terms cancel straight away because they involve a little cut at the top of the Jones-Venzel anapode, which comes up and collides with the S and kills it because it's a lowest weight vector. So when you expand these Jones-Venzel anapodes, there are actually quite a relatively few terms on either side, and you just see this sort of relation that we expected before, that 2 S's connected by 7 strands is a linear combination of annular consequences of x. So there's x with the count. Okay. We also get this other relation with x with two arcs as well. Now something important to notice here, which is sort of subtle but actually really relevant to both Haagerup and extended Haagerup, is that this relation here only holds in the shading that I've drawn. That is, if you reverse all the shadings in these pictures, there's no relation between those two diagrams. Now, this is something a little strange, and sort of for a generic principal graph with a split, you'd expect that there are actually both sorts of relations. The explanation for it is that when you write this guy in terms of two s's connected by 7 strands, in terms of annular consequences of t, one of those terms has coefficient 0, and so you can't then write that term in terms of the two s's. This is what I've said, that certain coefficient is unexpected in 0. It's not so unexpected. I mean, you can know this ahead of time by thinking about the principal graph and the working in terms of right-handed paper. But it's something special about this. What we can do, though, is take this relation here and substitute it into the second relation. Notice over here, there's an S that's shaded above and a single strand above. So we'll stick this guy. First of all, we'll expand out all the Jones-Venn light impedance there, and then substitute this term into there. We get some pretty ridiculous relations. So let me just write them schematically here. You have a generator T and 2 arcs above it. You can write it as some linear combination of terms with 0, 1, 2, or 3 T's in them. The T's are all at the top, and they're just connected to the bottom by some element of temporal lead. Say, for example, this element, x3 here in temporal lead, that's an element of how many strands does it have around the boundary? 16 times 4 plus 4, so it's an element of TL68. So you might think this is horrible, and specifying this x3 requires writing down however many coefficients the dimension of TL68 is. There's actually only one term in there, and it's relatively easy. These x's are not so bad things to write down. Okay, you should think of this relation now as letting you pull a T through a pair of strands. Imagine that you're in the braided case. You can certainly pull T's through strands by using the gradient to pull the strand over, and then using the Kaufman formula for a crossing to resolve all the crossings. This is roughly like that, but sort of much worse. You can only pull through pairs of strands, and the number of T's increases, which is sort of disastrous. The fact that the number of T's increases means that it's really not obvious at first how you use this to evaluate a closed diagram. Fortunately, I'm actually going to give you a short talk here. Fortunately, there's a wonderful piece of skein theory that shows you how to use this relation to evaluate an arbitrary closed diagram. It's called the jellyfish algorithm. This is a picture of some jellyfish in some lake somewhere in that sea. Okay. What do? We begin with an arbitrary planar network of T's. So here I have strands labeled by integers. That just tells you that actually there are 6 strands connecting this T with that T. And I've drawn in the shadings. Obviously, the shadings don't change when you go across any number of strands. So this is not goes with the same. So now, each of the T's, pick a path to the outside region from an unshaded region on each T. I've drawn this here where all the paths are just going straight up. But obviously, if you wanted to, you could be lazier. This T here is already at the boundary, so we could just put it out that way if we wanted to. But obviously, this algorithm has lots of choices, and we'll just make down the straightforward choices. Okay. Now we just float each generator to the surface using that relation from the previous page. So, for example, when I first move this generator up, I get some linear combination of different numbers of T's. So obviously by now I need to have a sum here, and this really could have 0, 1, 2, or 3 T's there. But it's still the same sort of diagram, and so I can keep floating things up. The number of T's increases and increases. And so I've only drawn 9 T's there. If you go back to the original one and look how many T's this is passing through, see how many strands. This passes through 10 strands. So if you use that relation 5 times, so maybe we have like 3 to the 5 T's resulting from that guy. It looks like it could be a bit of a disaster. But really it's all okay now, because diagrams of this form, where all the t's are in the outside region, are actually really simple to evaluate. The diagram looks like a polygon with some diagonals drawn in, so the vertices here with the t's are just drawn in two different ways. One, so it looks like the picture on the last slide, and I've just straightened out the polygon. And the point is just that any such polygon has a corner. Here's a corner, here's another corner, here's another corner. You can prove this in many ways, it's very easy. If you're at a corner, and the labels on either side add up to 16, at least one of the sides is labeled by an 8. And that means that somewhere in this picture, there are two t's, say here and here, connected by 8 strands, and so we can use the t squared equals the Jones-Venzel item relation to remove those two t's, reduce the number of t's in total. And when you do this, replace those two t's, the resulting diagram still looks like this. All the t's are at the boundary. You haven't, no t's have gone inside. You've never wrapped temporally strings around the outside or anything like that. So you don't need to use the jellyfish step anymore. You just keep looking for corners and removing pairs of t's. So the first step, we produce heaps of t's, and now I can just kill them pair by pair. I guess that's it. Yeah, we evaluate all diagrams, so we know that we've got a subvector planar algebra, so we know it's the right thing. Thanks. One more. Just
All right, questions, please. Just a quick one. So you can assume you can do the same thing with W and what will be